So, welcome everyone. Thank you for joining to our online workshop on valorizing renewable thermal energy, innovative renewable multi-generation energy systems for flexibility and sector coupling. Here today we have two European projects represented, the Region by Two project, for which I am the Communication, Dissemination and Exploitation Manager. I am Laura Perez, part of the innovation team at R2M Solution. And together with the nGEL project, we managed to organize this very interesting workshop that I hope all of you will enjoy and will have interesting questions. So just as an introduction, the Region by Two project, it's titled Next Renewable Multi-Generation Technology Enabled by Two-Phase Fluid Machines. It's an H2020 project that is finishing soon next year. And it had a budget of a little bit over 4 million euro under the core topic for developing the next generation of renewable energy technologies. On the other side, we have a more recent project, the nGEL project, titled Next Generation Flexible Three-Generation Geothermal ORC Plant, with also a budget of a little bit, sorry, maybe I mistook and it's repeated the budget. I didn't update that number, sorry. But it's under the core topic for a smart use of geothermal electricity and heating and cooling in the energy system. So today we have three representatives from each project that will be presenting their updates and insights from the projects, and then this will be followed up by roundtable discussions and Q&A questions that you will be able to ask either through the part that you have in the session here on the right. You will be able to post questions there, and we will try to address them all. So first we'll hear from Stefano Briola, the CEO and founder of Tifeo, an innovative startup who is the exclusive licensee for the technology and the thermodynamic cycle that it's being developed under the Region by Two project. Then we will also hear from Nicolas Leclerc. He's a research engineer and PhD candidate at University of Liège. And then finally, from the Region by Two project, we will have Michael Strobel, project manager at Dr. Jacob Energy Research. On the other side, we have the project coordinator of the nGEL project, Shahin Jamali, from Fraunhofer Institute on Energy Infrastructures and Geotechnologies. We also hear from Irem Erem, R&D specialist at Sorlu Energy, who's leading the demonstration activities in this project. And finally, we'll have Kevin Malin providing the insights as the director of GeoLearn. So without further ado, I will give the floor for the presentations. First, we'll hear the three presentations from our Region by Two representatives, then we'll have a short Q&A. Then we'll hear the presentations and insights from the nGEL project representatives, with also followed by a Q&A, and then we will go to a panel discussion where we'll have a few interesting questions, but we'll also, of course, want to hear any questions from the audience. So I will stop sharing now and welcome Stefano to the stage.
Okay, now I will share my screen. Can you see my screen?
Yes.
Okay, so good morning, everyone. My name is Stefano Briola, and I am the CEO of the startup Tifeo. We are involved in the H2020 project called Region by Two, which aims at developing the first prototype of our patented combined cooling, heating, and power technology, which is enabled by two-phase flow machines. So with this presentation today, I will provide you an overview of the main features of our patented CCHP technology. So first of all, Two-phase flow machines are innovative turbines and compressors that are able to operate with working fluid consisting of liquid phase and vapor phase simultaneously. In contrast, commercial traditional single-phase turbines and compressors are able to operate with working fluid consisting of only liquid or only vapor phase. So two-phase flow machines are key components in all our patented technologies. In particular, our patent portfolio consists of three concepts. The first one is the CCHP process and plant. The second one is the high temperature heat pump process and plant. The third one is the long-term energy storage process and plant. In each of these three patents, the concept that we protect is both the thermodynamic cycle and also the plant that realizes this thermodynamic cycle. In the next presentation, Dr. Leclerc will provide you more details about two-phase flow machines. The figure on the left side shows the schematic of the patented CCHP plant, whereas the figure on the right side shows the qualitative temperature-specific entropy diagram. So, the process and the plant can be ideally divided into two sub-circuits. The top sub-circuit approximates theoretical direct Carnot cycle, whereas the bottom sub-circuit approximates the theoretical reversed Carnot cycle. The working fluid is split into two portions at the point 1, and then the two portions are mixed together at the point 13. So briefly, in the top sub-circuit, we have two compressions, 1, 2, and 2 stars 3. 3 expansion, 4, 5, 5 star 6, and 7, 8. One thermal regeneration, the cold side 2, 2 star, and the hot side is 5, 5 star. The heat input from the heat source is 3, 4. And finally, the heat supplied to the user is 6, 7. In the bottom sub-circuit, we have one compression, 9, 10. One expansion, 9, 10. One compression, 11, 12. And finally, the cooling supplied to the end user, 10, 11. Finally, the process is completed by two heat sinks, 13, 1 and 1, 9. The electricity, the net electric power provided to the user is obtained subtracting the overall electric power of the compressors from the overall electric power generated by the turbines. The final remarks, the CCHP process and plant here described can work reversibly as high temperature heat pump. That is the subject of our second patent. The main advantages of our CCHP technology: high efficiency, because as we saw in the previous slide, the patented process is a proper combination of the direct and reversed Carnot cycles. Another advantage is the high operation flexibility. It means that the process is capable to fulfill the variation of the energy requirements of the users in terms of powers and related temperature, thanks to the regulation of several process parameters. Other advantages are modularity, scalability, the capability to switch on from the CCHP mode to the combined heating and power, I mean CHP mode, and combined cooling and power mode, CCHP mode. And finally, another advantage is the capability to use simultaneously different heat sources with different temperatures. So the market opportunities related to the users requiring simultaneously electricity, cooling power, and heating power are, let's say, enormous. We identified several applications in several fields, in particular industry, AI data centers, tertiary field, aerospace, heavy-duty transportation, and also residential. And in all these fields, our patented technology, of course, can be implemented. So more details about the market opportunities will be provided by Dr. Strobel in the next presentation. So thanks for your attention.
Thank you very much, Stefano, for your overview of the patent and technology. Now we will follow up with a presentation from Nicolas, going a little bit deeper on the two-phase machines, especially on the compressors.
All right. Hello, everyone. Can you see my screen?
Yes, it's not in full presentation mode, but...
Now. All right.
Yes.
So thank you, Laura, for the introduction. So I'm Nicolas Leclerc from the University of Liège. I'm still a PhD candidate, so I'm not yet a doctor, as Stefano said, but it's fine. But I'm soon to be. And today I will talk to you about a crucial topic related to the two-phase CCHP cycle that Stefano just introduced, which is the two-phase machines involved in the thermodynamic cycles. So here I will speak about two-phase scroll machines, because those are the machines that we have selected for the first prototype that we are developing within the European project Region by 2. But of course, this is still low TRL, and it's going to be developed maybe in the future with other kind of machines with higher power inputs, for instance, screw machines or even turbo machinery. But here we are speaking about volumetric machines, which are scroll machines for this project. So here I'm presenting the cycle with some example of operating conditions under which these machines are going to operate. The temperature entropy diagram here is a little bit different from the one Stefano just introduced, because we have made some change in the project in order to have something a bit simpler to implement because we are still low TRL. So the objective is to succeed in operating this cycle. And even if it's not the final cycle, it is fine as soon as we can prove that it's working. So for instance, here I'm taking the example of the compression 1 to 2. I can maybe use a pointer. It's gonna be easier. So this compression here, where I'm displaying the conditions. So it's going to be a little bit technical here, of course, but you need this to understand what are the challenge that we are facing in developing the cycle. So in those conditions, we are starting with a vapor quality, which is a mass quality of vapor. So basically, it's the mass flow rate of vapor divided by the total mass flow rate that we have at the inlet of this compressor. And you can see that eventually it's almost reaching the liquid saturation line of the diagram, which means that it is operating under strong conditions. Usually we are not operating volumetric machines with those conditions. But as I'm saying, it is only a mass fraction. And if you link a mass fraction that you can see here on the diagram with the volume fraction, which is actually the real volume taken by the liquid, by the vapor, here in that case, at the inlet of the machine, you can see that it's not so high. For instance, so it's not so low. For instance, here we have 40% of vapor in mass, but we almost have 100% of vapor in volume because the density of the liquid phase is way higher than the density of the vapor phase. This is just something that I wanted to mention. So it's not, so we still have actually a lot of vapor in the machine. Those are the prototype that we have developed throughout the project. So first, we have experimentally tested the commercial compressors with the, and we have modeled the commercial compressor working with two-phase refrigerant flows. And with the outputs that we got from the sensitivity analysis, we designed this scroll prototype, which has a high displacement volume, so it's higher than the commercial machines that we can find, a high built-in volume ratio, because we noticed that to get better efficiency, it is needed to have such high built-in volume ratio when working with two-phase flows. It has a radial compliance, so that if you have too much liquid stuck in the machine, you're not breaking the scroll mechanism, so you still have this compliance allowing to move the orbiting scroll. And we have an embedded pressure sensor that we have installed at the bottom so that we can check the variation, the evolution of the pressure inside the compression chamber and the discharge chamber, which is useful for model validation and to learn more about how could this prototype be improved in the future. So those are the performance, experimental performance that we obtained from the test of this machine that I just presented. So this is here only the case of a compressor, not the expander. Normally it's the University of Athens that was in charge of the expanders, but they couldn't present today. So here it's only the compressor mode. I'm presenting the volumetric efficiency, which represents how well the mass flow rate is, let's say, supplied by the machine, and the isentropic efficiency, saying how well the power inputs is used to thermodynamically compress the two-phase fluid. So regarding the volumetric efficiency, it is a bit lower than the commercial machines, and I will explain later why. And regarding the isentropic efficiency, you can see that when you decrease the inlet vapor quality, usually it tends to go down for several reasons. So here, the operating conditions I'm presenting is for an inlet pressure of 1.5 bar, an oil circulation ratio of 5%, and a compressor speed of 2,500 RPM. And so the conclusion from because we also needed to validate some models to understand why we have such trends in the efficiencies evolution. And so for that, we did a modeling campaign, we did the experimental work, and we managed to validate the models. And we came up with the following conclusions. So first is that scroll compressors are robust machines to work in two-phase regime. But as I said at the beginning, even if you have low mass vapor quality, it doesn't mean that you have low void fraction at the inlet of the machine. Working with two-phase refrigerant flows reduce the pressure ratio for a given volume ratio, which means that you can see here, the lower the inlet quality, you see that the optimal isentropic efficiency corresponding to a given pressure ratio is actually decreasing. So you see that the maximum here is going lower and lower when you decrease the inlet vapor quality. Two-phase compression creates irreversibilities due to the temperature difference between the two phases. So when you compress a two-phase fluid, the vapor phase is going to increase its temperature because when you compress vapor, usually the temperature rises, while the liquid phase is incompressible. So normally it's not going to change. And so you have heat transfer between the two phases, and the higher the temperature difference between the two phases, and the lower the resulting efficiency is going to be. And due to the liquids, the leakage gaps of the machine can be increased, and this is why you have this reduction of volumetric efficiencies. And my theory about that is that the tip seal of the machine is moving due to the liquid, and that's why we have a lower efficiency on that side. On the contrary to screw compressors, where mechanical losses caused by the liquid are important, this is usually something that we see because at the extremity of a screw, you can have speeds up to 50 or even 100 meters per second. So you have huge mechanical losses. Here, they are negligible in scroll compressors. So even if you have liquid, it's not going to increase the compression work. And so that was it from my side, and I hope we can have interesting discussion after our last presentation. So thank you.
Thank you very much, Nicolas. So after we heard from Stefano and Nicolas more on the technology side, now we're going to hear from Michael. He's going to be presenting the users and potential applications for the solution. In the meantime, you can, if you already have any questions for our presenters, you can include them in the Q&A box on the right. You can go ahead, Michael.
Thank you very much, Laura. Also, good morning, everyone, from my side. Thank you also, Stefano, but I'm such as Nicola also still a PhD candidate, not a doctor yet. I want to present now a little less technical topic on the analysis of user and thermal demands on the tree generation unit. The unit itself, as presented and patented by Stefano, is an interesting and innovative solution to use any kind of heat source, whether it is from biomass, from industrial waste heat, from solar, but also from geothermal, to use excess heat or renewable heat to supply any kind of users with heat, cold, and electricity. This is very interesting, and as Stefano already presented, there are various users that could be also of interest for the tree generation unit itself. But of course, it's also interesting to check, okay, what are the requirements from the users to the tree generation unit? So this was also in focus of the Region by 2 Work Package 8 activities on the exploitation, where the unit and the final product can be applied. What we investigated in was especially those 4 user types. So focusing on industry, residential, retail, and office use. Here's some characteristics for each of those types. So of course, industry is always a large consumer. Here it's interesting to create and build large products, large plants. Their demand, their thermal demand on heat or cold is less dependent on climate or on the change in seasons. Potentially, they have a high temperature heat demand, but still any heat from the unit can be used for preheating processes, which is which you can find across all industry sectors more or less. And of course, the industry itself is very interesting as heat supply and heat source to drive and run the tree generation CCHP unit. The individual users and office users, here it's more on private users, often also more small scale users. The thermal demand is highly affected, of course, by the seasons. So we have a high cold temperature demand in hot seasons, heat demand in cold seasons. And for retail, here we focused on such applications such as shops or supermarkets. The cold is usually supplied via refrigerators or freezers that are electrically driven. However, here we can directly via heat exchangers, for example, also implement any cold generated from the tree generation unit, for example. Also, for the retail, such as for the industry, we have no change in the demand or no high change in the demand in the different seasons. So these were the user types we focused on. But in reality, actually, here just an example for our city in Germany, you cannot or you won't find these user types completely separated in their location. So in reality, you find a combination of them. So especially when it comes to a plant size application of the tree generation unit, it's interesting, okay, how is the demand of especially the thermal heat and cold demand of the users, how is it linked with each other? How does it affect maybe also each other? So of course there are different user types, whether it's just for example city centers. There you have the office users and the residential, whereas in commercial sites, commercial parks, you find supermarkets, shops, and manufacturing companies, and industrial sites. So there is still, of course, a variation, but in general, you can find most often a combination of those. Here we checked different combinations. Now I want to present especially one which is called the Berlin mix in urban science, more or less, as it's based on the historic structure of Berlin, where you can find offices and residential users as well next to industrial sites, actually. This is very promising as to drive and run the tree generation unit, heat must be available, and waste heat is an interesting and also technically promising solution, as it's available more or less throughout all the year. No high changes in seasonal demand, such as from solar thermal. And here you can see how it may affect. So on the monthly capacity of heating and cooling, you can see that the demand for the industry in this case is more or less constant. Whereas, of course, for heating and cooling, there are high variations for the office use, but also for residential applications. And that for the office use, especially, again, you will have a high high cooling demand in summer times. So here we can already see how it may affect the annual operation of the tree generation unit, as the extraction and heat and cold supply from the unit and from the cycle directly affects all the other processes and components' behavior. So, for example, if we have in summertime extract less heat from the tree generation thermodynamic cycle, then we may have more energy, for example, to harvest or to yield electric output from the unit. It's also interesting that not only the mix itself and the combination of the individual user types, but also, of course, the location and the climate affects the overall performance. As here, just a quick comparison for how this Berlin mix of the same capacity, same sizes, where how the heat and cold demand may look like in Spain and Germany, for example. So here we can already see that climate also affects or will affect the demand and such the operation performance and maybe also the sizing of the unit itself. So the learnings are that the heat source, of course, is relevant. As industrial sites are an interesting heat source and heat provider to operate and drive the unit. Of course, the availability in time is also interesting. How easy is it to run and shut down, for example, the unit, or to reduce, for example, the mass flows to control more or less the capacity of the unit. Also, the system is very relevant, especially when it comes to thermal energy storages. Any thermal energy storage applied in the system will, of course, affect also the sizing of the plant and the unit. And potentially, it's also interesting to combine it with backup or peak load boilers. On the temperatures, of course, the higher the temperature in this case, the better is the performance of the unit and the cycle itself. So here, the unit may see competing technologies when it comes to especially the valorization of waste heat. Also, on the heat output and heat supply temperatures, is it, for example, the same for all users, or can it be adapted maybe within one unit itself? And on the cold output, industrial users may require, for example, for freezing or for shock frosting any goods or products. They may have cooler temperatures, and how it may affect or may also be combined with other technologies. So here there's also plenty of solutions and potential. On the power generation, we did not focus that much on the power generation or power demand of the individual users itself, as we assumed that electricity is always required. And with selling, for example, the electricity, you always increase the payback period, or reduce the payback period, increase amortization. So the conclusion and the next steps of this investigation is that both the user types and the combination, as well as the climate, is fundamental for the unit operation to say, okay, how to run and how to control the unit and the plant. The region by two unit and plant and cycle may be adapted in future times for each use case potentially. A more detailed dynamic analysis of the units and of the plant may be interesting to also involve the influence, for example, of the ambient temperature, how it may affect the cooling potential and the cooling performance of the unit itself on the heat excess side. And investigation on the flexible heat supply would also be interesting, especially when it comes to the system approach and the thermal energy storage topic, how the system performs and behaves when it is combined with a variable and viable heat supply source such as solar thermal. Thank you very much.
Thank you very Michael. Thank you very much, Michael, for your insights on the potential users for the region by two technology. Now we have time for a short Q&A. I don't see any questions on the chat box, so please feel free to add them there. If not now, we can address them later. To not further delay, maybe we can address one question and then we can proceed with the next presentation. So I can ask Stefano, since the project will be finishing soon in February next year, we're approaching the final stages of the Region by Two project. What are the planned next steps for TIFEOS to face machinery? Can you give us some insights on your next steps?
So yes. So thanks, Laura. So during Region by Two, we developed volumetric machines, in particular scroll type. But these machines can be useful only for, let's say, small powers. So in the order of a few kilowatts or 10 of kilowatts. But the goal of our startup is to fulfill the energy requirements in the medium scale and the large scale. So for this reason, we will develop two-phase turbo machinery. I mean, dynamic compressors and turbines. So we have in our startup already the know-how to do this, because one of the co-founder was working in this topic in Institut Français of Petrol and also in Total. So we will use his knowledge as starting point to develop, let's say, our concepts. And in this way, we will be able to fulfill medium scale and large scale powers in different field of CCHP.
Thank you very much, Stefano. Hope good luck and see how this evolves in the coming years. Are there any other questions for Stefano, for Nicolas, or for Michael at this stage? Not, we will proceed. So now we've heard from the Region by Two project, which, as you've heard, it's a low TRL. It's a research and innovation action, and we are performing experimental tests at lab scale. And now we will hear from nGEL project. This is an innovation action at higher TRL, also developing three-generation technology based on geothermal energy. So I will give the stage to the coordinator of this project, Shahin Jamali from Hofer, to give us an overview of the project, and then we will also hear from Irem, Eren, and from Kevin Malin on more specific details. Please go ahead, Shahin.
Thank you very much, Laura. Really appreciate your kind introduction. I will try to share my screen right now. Okay, just a question. Is it working? Can everyone see my screen? Okay, so thank you a lot again, Laura, for the nice introduction. So basically, as Laura mentioned, I'm Shahin Jamali, and basically I'm working as founder of IEG, and we are coordinating the nGEL project. So how we are going to present the nGEL project basically will be as followed. I will try to give you a very brief and general overview of what the nGEL project is and what are our goals. Then my good colleague Irem will go into more technical details of how we are going to implement the technology, and ultimately Kevin will discuss about how we are going to exploit and impact the industry. So the nGEL project basically stands for Next Generation Flexible Tri-Generation Geothermal ORC Plant. So basically the name, as it suggests, we are working towards having a flexible ORC plant that is basically focused on tri-generation of geothermal energy. To give you an overview of the project, so the project is going to run for 48 months. We have started last year, so we are more or less in our second year of the project. We have been part of the Horizon Innovation Actions, and as Laura mentioned, so we are basically aiming at higher TRLs. We have been part of the cluster for smart use of geothermal electricity and heating and cooling in the energy systems with having 6 main milestones, which I will go into the details later on. And within these 6 milestones, we are trying to develop 3 main key technologies. In total, we have had 5.2 million euros of total costs, and the EU contribution actually have been 4.3 million. We have 7 key partners, 2 Fraunhofer institutions, and 6 other partners that basically make up the consortium. So just to give you a little bit of an overview about our mission. So the core mission that we have within nGEL project is basically to transform geothermal ORC power plants into a flexible trigeneration system that is able to produce electricity, heating, and cooling while using an AI EMS system to intelligently do that. So what are we focusing on within this core mission is basically the heating and cooling in the EU is more or less account for 46% of the energy consumption. Considering this number, only 18% is met by renewables. So within the nGEL project and all the other projects, actually basically everyone's trying to target this untapped potential of low to medium temperature geothermal resources, which is basically available within Europe. So that's also one of the parts of the core mission. And to add to that, we have calculated and we have estimated that if we could apply across the EU the nGEL technology, we could more or less meet about 4%, my apologies, of the EU current annual heating and cooling demand, which would be actually a big economic save amounting up to 9.6 billion annually. So this is a big number, but that's more or less what we try to basically achieve through scalability. So having the scalability potential in mind, what is the demand at the moment that defines our core mission? So there are multiple challenges at the moment across EU. The first one being the energy consumption gap. So heating and cooling, while nobody pays that much attention to it, but it represents 46% of EU energy use. So that's a big number, almost half of the energy used within EU, but the renewables only cover a small fraction of this demand. So this is one of the main challenges to increase the amount that renewables contribute to the EU energy consumption. The second is we have a big reliance on fossil fuels. Basically, natural gas is the primary source, which more or less creates economic and environmental vulnerabilities and instabilities, as you may all know. Adding on top of that, there is grid instability because of this reliance. Then at the same time, the current renewables, the main popular ones are solar and wind, which are intermittent and they bring challenges to the grid stability because they are intermittent. And on top of that, Europe has a lot of abundant low enthalpy geothermal fields, but they are basically underutilized, especially when we are thinking about binary ORC plants. So considering all these challenges, what we think is needed or required to solve these challenges ahead is basically coming up with a flexible and at the same time scalable renewable energy. And our answer to that is basically the tri-generation system within the nGEL project to provide flexibility for various energy demands. At the same time, while we are talking about grid and stability, we think that real-time demand response would be something to solve this solution. And the proposed solution here would be an AI-driven, based on AI models, EMS that basically integrates the cold, the hot, and electricity production to bring grid compatibility and supports the day-ahead energy market, basically thinking about the future and implement it in real time to basically meet the demand response. And the third one would be basically the scalability across the EU. And we also try to target the sedimentary formations, and that basically can be implemented widely with existing and also new ORC infrastructures that is underutilized within the EU. So just moving ahead, so those were basically the answers, and in more details, how we are going to do that through 7 main pillars. The first one, what we want to do within the project, the main and foremost one is to design a flexible geothermal ORC power plant with tri-generation capabilities. That's the keyword here. And at the same time, to do that, basically we are trying to develop multiple other technologies. The first one being to design and develop a cold thermal energy storage system, and we have already within previous projects have developed and designed a hot thermal energy storage. So we are focusing on two types of energy storage systems. At the same time, to basically bring that flexibility, we have been developing a control strategy for demand side management. At the same time, to provide an EMS, energy management system, for the flexible ORC, while increasing reliability of ORC against different ambient temperatures, especially the high ones, because it affects the ORC reliability. And all in all, bringing all these digital technologies into an AI-driven digital twin that will integrate everything, and with the big aim of ensuring environmental sustainability. So that's what we are trying to achieve within those objectives, which basically results into three main things: AI-driven EMS, while bringing all the digital technologies, hot and cold thermal energy storages to basically have a storage solution while ensuring energy availability during peak demand. So when the demand for example, the cold thermal energy, so to speak, let's just say in a hot season, when the demand is high, how do we basically respond to that within a district heating network? Basically, that would be through the cold thermal energy storage, which Irem will basically describe more on how we are going to achieve that. But that's how we are going to solve that problem. And how do we basically create these energies to be stored? That's basically using absorption chiller and heat exchangers to enable cooling and heating while enhancing multifunctional use. So absorption chiller for the cold thermal energy storage and heat exchangers for the hot ones. So that's basically how the network will look like within the tri-generational system. My apologies. So this is more or less my last slide, which basically will more or less transition to what Irem will be presenting on the methodology. So we will have a digital twin integration into the system, which primarily is focused on AI-based simulation models to optimize the ORC system, and at the same time, the day-ahead market predictions. The second one is basically the cold thermal energy storage, which we are basically developing a novel technology here for enhancing grid resilience. The demand side management, which would be basically a responsive energy solution to say or predict what should be the optimized energy output to match the grid demand. And we want to also manage these three through a flexible environmental sustainability through demand side management. So, and this would be also what Kevin would be focusing on, basically what we are going to be having as expected outcomes. So we want to reduce capital and operational costs to bring cost efficiency while being environmentally and socially sustainable by lowering CO2 emissions. At the same time, we want to increase ORC competitiveness within the market and bring energy security and grid resilience through basically all the things that I just described. So this will be what the next presentations will focus on. So I will try to basically finish it here. We would be thankful if you could join us through any of our channels, through Facebook, LinkedIn, Twitter, and YouTube. We try to be very active, and also on our website, the newsletter. It would be really great to have more conversations and also connections through all of you. So I will try to wrap here and give the floor to Irem. And thanks for listening to the presentation.
Thank you very much, Shahin. I take this opportunity to say that the slides will be shared with the participants, so they will be able to access these details that Shahin is presenting now. So thank you for the nice overview of the project. Now I give the floor to Irem for the more specific demonstration activities that are being performed in nGEL project.
So thank you, Laura. Thank you, Shahin. I will try to share my screen. Please let me know when you see it.
Very clear.
Okay, perfect. So thank you, everyone. Thank you, Shahin. Thank you, Laura. And thank you, Region by 2 team for a very fruitful presentation, let's say. Welcome to my presentation. I want to keep it less technical, but a bit, let's say, explanative. I don't know in English. I hope it will help you to understand the project in a short way. My name is Ira Eren. I'm an R&D specialist at Zorla Energy. As I said, I will try to keep this session short but meaningful, and I hope it gives you a clear picture of what we're doing in Angel Project. So normally I'm explaining from the beginning what geothermal energy is, but I assume you already know what is that. But to simply mention that we are using the Earth's own heat. So by utilizing this heat, nowadays we are using this heat for many purposes, and more recently, electricity generation. So when it comes to power generation from geothermal power plants, the heat naturally rises toward the Earth's crust, and the type of plant depends on the temperature, pressure, and chemistry of the geothermal fluid. And of course, economic factors play a huge role. And the type of power plant mostly depends on the temperature, as I said, but not only the temperature itself, the mass flow, the pressure also play a big role. And I will go more detail, but to understand what Angel Project is, we need to understand, I think, the power plant types, because in Zorla Energy we are using triple flash combined binary cycle, but this project is ORC based project. So we have medium temperature in Zorla Energy's plant, and in the medium temperature we can use binary or organic Rankine cycle. But since we have combined cycle, we are trying to let's say implement all the technologies that we can do. So the three main types of geothermal power plants: the dry steam plants use the steam directly from the well. Flash steam plants let part of the water vaporize as pressure drops, and binary or ORC systems transfers heat from the geothermal brine to an organic fluid, which then drives the turbine. And ORC systems are especially suitable for moderate temperatures and cleaner operations, which is why they're common across Europe. And however, as I said before, Zorla Energy's Kızıldere power plant, we operate our system as triple flash combined binary cycle. Speaking of Europe, we have seen a growing interest in our geothermal thanks to renewable energy targets and heating and cooling needs. But this growth also brings new challenges for the grid. Maintaining a stable frequency essential for every power system. And as renewable sources like wind and solar fluctuate, balancing supply and demand becomes harder. And geothermal plants, however, operate continuously and cannot simply shut down or turn off the system or ramp up, which makes flexibility a key challenge. And this challenge is exactly where our project Angel comes into play. Speaking about challenges, across Europe, as Shahin already mentioned, but I will try to explain shortly again. Many geothermal systems, especially ORC-based ones, face performance drops in summer months, and during this high ambient temperatures, air-cooled condensers becomes less efficient and causing power output to fall by as much as I remember 55%. So in Angel Project, we aim to minimize that loss and make geothermal plants more adaptive and efficient. So what we're exactly developing, our goal is to build smart, flexible geothermal ORC system that can provide electricity, heating, and cooling on demand. To achieve this, we are combining state-of-the-art technologies with new design concepts, an absorption chiller to support cooling during hot conditions, thermal energy storage systems for both hot and cold operations, and a smart control platform, the storm and energy management system. And these systems will analyze data, forecasts, and grid needs to operate the system efficiency. So we have 7 work packages within this nGEL project. In work package 1, we're collecting the requirement analysis and specifications. In work package 2, we are focusing on thermal energy storage part. Work package 3 handles the control strategy, and work package 4, as Zorla Energy, we are involving on this part mainly. We will test and validate the system in real operating conditions. Work package 5 addresses sustainability and awareness, and 6 and 7 is basically in every project is the same. So now moving on to our demonstration cases, which will show how the concept works in practice. Initial concept design of the system, you can see on the flow diagram. Main goal is to succeed in implementing a number of technologies in one system, combining innovations and creating reference for investors within the growing geothermal market in Europe. So our goal is to flexibly provide heating, cooling, and power generation. And this will be achieved by utilizing the heat source, which in our case comes from the separator outlet and of the power plant, the real power plant itself. And to ensure clean fluid reaches the sensitive equipment in the system, we will use a heat exchanger for thermal energy storage, as well as an absorption chiller and their corresponding loops. And for district heating, no additional heat exchanger is needed since the district heating system itself acts as a robust heat exchanger that can handle continuous cleaning. And our control system, supported by the EMS system, will determine the route of the flow should follow. Initially, the process will involve storing heat in the thermal energy unit. And then, depending on the grid requirements, this stored heat can be supplied to a secondary ORC system. And if there is a cooling demand, the heat will be directed to the absorption chiller instead of storing it. If heating is required, then instead of heat exchangers, heat exchanger 1 and 2, I don't know if you can see, maybe I should use my pointer. Yeah. Heat exchanger 1 and heat exchanger 2 will operate providing heat to district heating and district heating systems or greenhouses, let's say. And additionally, cold thermal energy storage, I'm not sure you can see it or not. The cold thermal energy storage unit will be used to test the cooling storage capabilities and further increase the system flexibility. So this is our demonstration case basically. And we have second demonstration case, which can be seen on the figure. It is the ORC module that we will implement in this project. And in the second demonstration, we'll focus on system flexibility, showing how we can switch between heating, cooling, and electricity depending on demand. The system will use heat from the separator outlet and through the EMS decide whether to store it in the thermal energy storage unit, send it to a secondary ORC, and direct it to an absorption chiller for cooling, or use it for district heating and greenhouses. We'll also integrate a cold thermal energy unit, as I said in my previous slide, to test cooling storage capabilities and further increase stability. So I have so many limited time, but I wanted to keep it short but clear. I hope it is well understood, understandable, let's say. So in short, with nGEL project, we want to prove that geothermal plants can be flexible, not just constant baseload producers, and they can respond real-time energy needs, generating power, heating, and cooling when required while operating sustainably and efficiently. And thank you for your attention and interest for our project. I'm giving the floor to Kevin. If you have any questions,
Thank you, Irem. I encourage everyone, if you have questions, to put them on the chat, and we'll have the Q&A right after Kevin's presentation. So I give the floor to him. Let's see. Yes.
Good morning, everyone. Can you see my presentation?
Yes.
Good. The sharp-eyed amongst you will realize I'm not Laura Perez, despite the little logo in my photo. Thanks to all the presenters so far, what I want to do now is just really capitalize on all the research and the innovation that's being done, and think, why are we doing this? What's the importance? How important is it to Europe and more generally into the rest of the world? Because I think the key thing we're trying to do here is reduce carbon. We have a 2050 goal of reducing carbon to zero. So when you actually look at all the research that's being done, we're all aiming for the same goals, I think, but we're trying to get to them in slightly different methods. I was really fascinated by the Regen by 2 presentation, because it used a lot of technologies quite incidentally that we're using in other parts of actually in drilling at the moment. So my background is I've been looking for energy for the last 50 years. Started off with oil, then gas, and now geothermal. All of these technologies we talk about the transition. Anybody who's in our industry will still realize we're searching for oil and gas and we spend a lot of money on researching for oil and gas. So we need to catch up here. And I think because this whole meeting, these 3 days, are looking at sustainability, we realize that what we're trying to do here is, we're trying to reach a goal that may not be reachable, but if we don't attempt to, then we're going to fail miserably, and our children and your children will all face a very uncertain future. So for those of you listening who are not from this particular sector, and I hope there are people who've come to see what it is we're doing and the type of work we're doing, and anybody who's looked at the entire program will see it's a very varied and diverse number of presentations, people looking at different things. But again, I think we're all looking to find a sustainable goal. So renewable energy, we call it renewable energy. Yeah, wind blows, turns turbines. Let me move on. We all see them. We drive around the countries, we fly into airports, we see wind turbines all over the place. It takes kinetic wind energy, turns a blade, produces electricity through a turbine. That's then run through copper wires, etc. We all know this, but it's quite inefficient, because if the wind's not blowing, we don't have any turbines turning, and if the wind's too high, we have to stop them so they don't catch fire. So looking at the typical sort of efficiency of wind turbines, 25 to 45%. So we're wasting a lot of money, possibly, in making turbines. So what we're trying to do is make them more efficient, make them so we can store energy from them when they are producing it, and we don't need that energy. We want to be able to store it. Both previous presentations from our friends at Region 2 and from Irene and Shaheen shows what we're trying to do, one with geothermal, one with two-phase compression systems, etc. We're all aiming at the same goal, and there's lots of things now around storage, lithium brines, making huge batteries. How efficient are they? So we're taking electrical energy, storing it as chemical energy, turning it back to electrical energy. There seems to be a lot of wastage in that. So where we have a heating and cooling demand, do we really need to keep changing the nature of that energy? Can we just maintain it as a heat for heating buildings and then take it away as waste heat and store it so we can recycle it all the time without having to change it? Solar PV, you can see there, it's got quite a footprint. We're seeing these super sort of solar power plants now in places in sort of North Africa where they've got deserts, etc. We're moving them away from the centers of urbanization where we need the power. So we're building in sort of inefficiencies into the system. We use a huge amount of critical raw materials in making solar panels, not least, and this is a particular sort of one to my heart, is the mining for sand, because you need a certain quality sand for the quartz to make the glass panels. All these have a detrimental effect on the environment. So we want to make sure, and I use this sort of phrase, 300 years ago when we decided to burn coal because it was going to change the world, and now here we are today, looking at ways to mitigate the burning of all that coal and fossil fuels. But we want to make sure that we don't create in 100 years' time similar problems for our children. So we want to be able to think differently, and and I think the Regen by 2, nGEL, and you'll see a lot of other projects in Europe, really brilliantly funded by the Horizon 2020 fund, where we're looking to try and prevent those sort of things happening again. The other one to me, and this is again really it's a focus of mine, because I've been we've been involved in lots of drilling and grouting for these huge dams, and if you live downstream of one of these big dams and somebody suddenly cuts off all your water, it has a really impactful effect on you. This is happening. There's a Renaissance Dam in Ethiopia, and that's taking huge amounts of water away from the Nile system. And again, it's this law of unintended consequences, and I think again, when we start to look at sustainability, that's what we need to be thinking about. Whatever we do, we must be able to sustain it for the good of everyone. There are 8 billion people on this planet. There are scientists and social scientists, etc., say we have a planet designed for far less people. So we need to make sure that whatever we do is efficient, that we're not wasting things. Again, you can see that construction there, huge amounts of concrete. I think cement, the production of cement, it's about 8% of the world's CO2 outputs. They're starting to look at, lower those by carbon capture and storage, but again, that requires huge amounts of energy. So what let's be thinking, in a better way of how we do things. And projects like nGEL, projects like Regen by 2, that's what they're trying to do. They're trying to make these things more efficient, more sustainable. The ORC, and I think Shaheen and Irene gave a very perfect overview of what it is we're trying to do with organic Rankine cycle systems. Shaheen pointed out, throughout Europe, we have, quite a large resource, medium temperatures up to, say, 150, 160 degrees, where we can utilize those. If we can make those more efficient, as we're trying to do with the nGEL project, we get better usage, and that we have this sort of chance now to get 3 for 1. Those sort of offers you get in the Lidl and the Aldi supermarkets through Europe. Buy 1 get 2 free. So that's what we're trying to do in sort of unscientific terms. All that energy that the Earth is presenting to us, we want to be thankful to them, and use that energy in a smarter way. Cold storage, hot thermal energy storage, and electricity production. The interesting thing is, and the European Union have just reproduced this net zero innovation action. There's very little talk of geothermal in it. It's all to do with power production mainly, because it's very easy for all of us, to be honest, to understand what a kilowatt of electricity means, whereas, kilowatt of heat doesn't mean a great deal to someone, and they just think, oh, I turn my heating on, I'm warm, I turn my heating off, I'm cool. So trying to educate people, and I mean, this is across a very diverse sort of population throughout, not just in Europe but throughout the world, is to understand that power it comes in various forms. We're starting to see, and everybody knows this, these huge data centers, and I mean, data centers are, every country wants them. They're trying to chat the Googles and the Microsoft, Amazon. They want their big data centers. Interestingly, people like Google and Amazon are investing in geothermal exploration and power purchase agreements. The Fervo Energy in working in Utah and Nevada at the moment, they're aiming to sell most of their power production to, I think it's Microsoft probably. So that sort of use of energy is increasing, which means if we don't make the rest of the energy system more efficient, then the general public and other industries are going to be left wanting for electrical power, and that's quite a serious thing. And I did read an article the other day where North Africa, the surge in electrical demand for North Africa alone is just colossal. So we want to be making these things far more efficient and sustainable. This is what we're trying to do in nGEL, and we see with our friends at Regen by 2 and lots of other projects, we all have the same goals. We want to make our innovations not just for geothermal, where we see opportunities to share the research and the validation of the work that we've done. We want to take it out more generally into the industries. And I think for those who were paying attention, and it was quite a lot of sort of very scientific talk earlier on, that there's huge, some amazingly clever people that are having inputs into this to solve these problems. So I'm just trying to sort of make it a little bit more understandable for what we are trying to do here, and as to why Horizon 2020 generally is funding these sort of research and innovation projects, because they are very, very important. Shaheen mentioned this earlier on in his presentation, but I think, that just sums up that's probably one of the key factors. We can, 4% of the EU current annual heat demand, which is 9.6 billion euros per year. I mean, that's a stunning numbers there. So, once we get this system fully commercialized, we will be knocking on every single geothermal plant throughout Europe. And the picture of the surfer, by the way, is just because I live next to the ocean and I surf every day. That's the only reason it's there. So I spend a lot of time sitting on the beach, waiting for waves and thinking. So that's it. And Aren and Shaheen, they shared their contact details. There's some the codes and that you can scan, and as Laura says, all these are going to be shared. I'm not sure mine will be worth the second view, but I hope what I've just discussed here is food for thought as to why all these things are getting done, how we can make it sustainable, how we can hope that Europe by 2050 is a great place to be. We've solved the carbon issue. We're starting to reduce the climate effects of sort of greenhouse gases, and we got another 4.5 billion years to go in our futures. Thanks everyone for listening.
Thank you very much, Kevin, for giving us this overview of, besides the more specific technical objectives of the projects, what are the overarching goals that we're all trying to achieve. So now, since we started a bit late, we are almost reaching the end time of the session, but I hope that everyone is okay with staying a little bit longer for some discussion. So now we have the Q&A session for the nGEL project. I feel our audience is being a bit shy, but I will ask a question. Also, I encourage anyone else to ask any questions. Of course, we'll have the contact details afterwards if you want to reach out to any of our speakers. So in the nGEL project, you are deploying this AI-driven MES. So the question would be, so when deploying this AI-based control in geothermal, the algorithms, are they or should they be targeting more the efficiency of the system, maximizing the efficiency, or targeting the market responsiveness and the demand needs? Well, how are you balancing these two objectives within the project?
So maybe I can give more or less a brief overview, and thank you a lot, Laura, for a nice question. So basically, what we are trying to achieve here is to pursue a hybrid market-aware, efficiency-driven AI. So basically, we are developing multiple AI modules that will be unified under one umbrella, that will not solely basically work for increasing the thermal efficiency, which is what we are trying to do for the ORC, but at the same time to also bring market awareness and day-ahead predictions to basically make a hybrid version of having efficiency and at the same time market responsiveness merged or forged together as one system. There are multiple systems being developed, but they will be unified under one umbrella at the same time to achieve both at the same time. And that's what we believe would make this or enable us to do the tri-generation effectively.
Thank you, Zain, for the insights. Very interesting and relevant that both objectives can be targeted at the same time. Please feel free if any of you have specific questions for each other. Now I will make a more general question that I think applies to both projects. So, and any of you, I think you can provide your insights. So what do you feel are the main barriers that you are facing for, to achieve higher efficiencies, to achieve the goals of the projects? On the one side, we have the technical development. So I know in the Region by Two project, since we are in low TRL, the technical development could be a higher challenge than, for instance, the come to the market or the regulation and how to convince the users and the regulators to trust on our solutions, but also the nGEL projects more advanced and maybe more on that stage. So I just want to hear the perspectives on what are the barriers, what are the next step or research directions after the projects to overcome these barriers.
I can just give a very, very short answer to this, Laura, and I think it's a great question. So we have had technical developments planned within the project, which more or less seems plausible at this time, and we are achieving the targets. But what could be basically a barrier, or what could come as the next step, basically would be market and regulatory acceptance. So let's just say once we have the technology developed, so how can we provide reliability and safety of the AI features, also working within GDPR rules to have basically the AI in a trustworthy manner, and then as the next one, basically thinking about how we are going to integrate the technology and also make it acceptable within energy and electricity market, and how the regulations play a role into integrating all these technologies. So I think as soon as the technology development, I think maybe my good colleagues within the other project also can comment on that, but I think that would be the next step on how to bring the technology into an acceptable regime that can be integrated into district heating networks or other applications. That would be basically my idea or my perspective on it.
Thank you, Zain, for your perspective. Not sure, Stefano or Nicolas, you want to also share your insights regarding maybe the more technical related barriers or any other barriers you would like to share, and what would be the perspectives on how to overcome them in the coming years?
So yes, Laura, what I can say that in our case, the barrier are more technological, because it's the first time that two-phase machines were implemented in energy plants, in new thermodynamic cycles. So this is very big challenge, but we are confident that we will be successful.
Thank you, Stefano. Nicolas, since you're working on the ground on this, what do you think would be the next research directions to solve these technical challenges?
Well, yes, I can only agree with Stefano, as we have been facing a lot of issues since the beginning of the project. So the technical barrier is there, and we have to find some way with research to break them and to try to innovate and making this technology possible to be used in the future and efficient at the same time. So you need to have a technology that works and that is more efficient than the technology that already exists. So it is quite challenging. But yes, the only way I see to break those barriers is to keep searching, and this is well, something that we are currently doing. So I think everything's going well so far.
Thank you. Not sure if anyone else wants to share any more insights regarding the barriers.
Just one interesting point. When we were looking at the nGEL project and proposing it, we spoke to a German ORC plant, and we said, look, we can increase your efficiency. You will be better off, etc. And their answer was, I get paid 274 euros per megawatt, whether I'm producing electricity or whether I'm not. So why do I need to save any money? And that was quite a stunning, oh dear, what are we trying to do here? So and I think both of you have actually touched on it with the regulatory thing. If we pay somebody just to either produce or not produce, whatever, I mean, it does have a very tough effect on the market. So from the technology, someone's got to buy your technology because it's going to be a cost saving for them. It's going to be a benefit for them. But when you have people saying, well, actually, I still get paid whether I produce electricity or not, then that's going to be a significant challenge. And so I think that's getting people to understand that what we're doing is actually, although if they are getting paid the 274 euros per megawatt, then we need to explain to them, well, you're still going to get 274 euros, but you're going to produce it for 200 euros. So there's a sort of a steep learning curve on how people perceive what we're doing and the benefits it's going to bring to them, this sort of what's in it for me sort of attitude. And then the other one is, we need to create a fear of missing out, that if people don't adopt our technologies, then they're going to be missing something. So I think there's a big social and sort of commercial aspect that we need to address, generally across all these technologies. And even with the low TRL levels, regen by 2, I mean, it's technically, it's very advanced. I mean, if you looked at it, you go, well, that's really advanced. And to think that's only technology readiness level 3 to 4, that's quite a sort of something to think about in terms of how people are going to engage with that technology in the future.
Thank you, Kevin. Indeed, regarding how we need to provide recommendations to the regulators, to the market, to also adapt the context to so our technologies have the maximum impact. It also needs to be taken into account that, at least in the Regen by 2 project, the technology, the way it's designed, the way it's it will be coming up in the future depends on the type of user we will be targeting. For the moment, we see that the industry might be the one of the main users to target. Also, Irem, you mentioned potential different users. So just wanted to hear perspectives maybe now from Irem and Michael regarding if you see industry as the main users to target, or if there would be a way to also on the way how we frame and position the technology in the market, also with other potential users, or it should be really targeted at industries.
One more thing that I think it's very interesting that both projects follow 2 different paths actually to deliver heat, cold, and power. As from my perspective in nGEL, it's really a CCHP plant combining different units such as ORC, absorption chiller, and geothermal. Whereas in Regen by 2, it's more on the tree generation unit. So one cycle is producing or supplying everything. So I think it's very interesting that there are these 2 different paths in general. So I would also be interested for nGEL, for example, if the ORC unit supplier and the absorption chiller technology manufacturer, whether they are also part of your consortium. But on your question, Laura, I would say it's also a little bit different for both projects and technologies. As for the region by 2 unit, we need also to address the heat source. For nGEL, it's quite clear with geothermal, but for region by 2, we need to address also the heat source, whether it is solar thermal, geothermal, or waste heat. And I think industrial waste heat is a real promising heat source for this technology. And on the supply side, I would, yeah, it's very open actually. It can be various uses, but regarding the temperature ranges, we will demonstrate with a prototype within the project. I would say to focus especially on building applications for now and the rollout of the technology, because the cycle and the technology itself can be adapted for different temperatures using different working fluids, for example, because the idea of the patented cycle is not limited to what is demonstrated within the project, but can be adapted for further applications.
Thank you, Michael. Irem, you want to share your perspective on the applications and users for the nGEL technologies?
So maybe I can add a few more sentences. Thank you, Michael, for your comments. So actually, in Zorlu's plant, we are already using triple flash and combined binary cycle. But the challenge is to do it flexibly. So in Turkey, we have several geothermal power plants in similar areas because of the tectonic activities. And Zorlu's plant is the one of the largest one within the Europe. So okay, we are producing electricity and we have cogeneration plant. And to add one more system is making us flexibly providing cooling, heating, and electricity generation at the same time. And from my side, I think it's the biggest challenge because we are doing this. Okay, we have waste heat, we have heating, we have power generation, but we are producing again and again, and there is no turn off in geothermal. So in our site, we have no, let's say, district areas, but we have very so much greenhouses around here. So in greenhouses, we are providing waste heat, but I think out of control, let's say, because if they don't want it, we are providing it. If they want it, we are providing it. So make it flexible is one of the biggest issue and one of the biggest challenges in our project. In my site, as a site operator, I think Shahin or Kevin has different perspectives, but as a geothermal site, it is the biggest challenge in my perspective.
Thank you, Irene, for your perspective. I want to, since we're already 10 minutes over the time, I don't want to also keep people longer than it should, but I want to give the time for anyone to share any final thoughts or reflections, and then we can close the session. And okay, so thank you very much all for joining today, for sharing the very interesting developments that are being carried out in both projects. I thank the audience that we've had here today online. I believe there is very good perspectives for these three generation technologies, providing flexible energy, both heating, cooling, and power simultaneously. We are both projects targeting this challenge on making it flexible and high efficient. So hopefully we'll hear nice final results from both projects. We encourage further collaboration and synergies to explore how we can learn from each other. So I want to close the session here, thanking everyone, and we will make this video available and also the slides for anyone to be able to reach out to the specific partners of the projects with for any interest you might have on what we are developing, and also other partners that are not part here of this session, but we have very nice consortiums working on very interesting research fields. So feel free to reach out and engage on our websites and social media to keep updated about the advances and the latest developments. Thank you all very much, and let's keep in touch. Thank you.
Thank you.
Thank
Bye.
you.
Thank you very much,
Bye.
Laura.